Imagine this. You've got a complex digital city, billions of transistors working together, and suddenly the traffic lights stop working. Or signals get totally garbled, you end up with system-wide failures, corrupted data, just maddening deadlocks.
Yeah, that's a pretty good analogy for the kind of chaos we're diving into today in chip design.
We're going to unpack one of the most fundamental, yet sometimes really frustrating cornerstones in modern system-on-chip design. That's the Advanced Extensible Interface, or AXI protocol.
Right. And it's not just some obscure tech term. It's basically the communication backbone. High performance, royalty-free, connecting all those different specialized blocks, the IP blocks, inside a complex chip.
It came out around 2003 with AMBA3, then got refined in AMBA4. And it's really built for speed and efficiency, right?
Right.
Things like independent read and write channels, handling multiple transactions at once, even completing them out of order.
Exactly. But here's the kicker, the real paradox. That very flexibility, the thing that makes it so powerful for high-performance designs, it also creates this, well, labyrinth of potential pitfalls.
A minefield, almost.
Pretty much. If you don't manage that complexity meticulously, it can seriously undermine the whole system's reliability. Engineers often talk about AXI integration turning into a debugging nightmare.
And these nightmares, they often come down to fundamental protocol violations, don't they?
Very often. And it doesn't matter if the failure starts with the manager, like the main processor kicking things off, or the subordinate, say, a memory controller responding. The result can be just as bad. Deadlocks, corrupted data, the whole bus just stalling out.
So our mission today really is for you, the curious learner. We want to shed some light on these common AXI debugging challenges. We're going to focus particularly on two big culprits, those failed handshakes and misaligned bursts.
And we'll bring in some real-world war stories too, tales from engineers who've been in the trenches battling these exact issues. Hopefully that gives some actionable insights, some solid strategies for preventing and fixing these things.
Think of it as your shortcut to understanding a really critical but, yeah, often frustrating part of modern hardware design, hopefully full of some aha moments.
Let's hope so.
All right, let's start right at the beginning. To debug AXI effectively, you need more than just knowing the names of the channels. You need to grasp why it's built the way it is. What's the core architectural choice that gives it power but also makes it tricky?
Yeah, good question. The absolute core idea is that AXI uses 5 independent communication channels. You've got read address, read data, write address, write data, and the write response channel.
And they all have distinct signal names like AWADWare for write address, WData, RESP.
Exactly. And that independence, that's its superpower. It allows for incredible concurrency doing multiple things at once. But it's also where the hidden problems often start, especially if you don't manage the timing between those independent channels just right.
Okay, and building on that independence, AXI connections are point-to-point, right? Linking a manager, like maybe an ARM processor, to a subordinate, like a memory controller.
Precisely. And that structure enables what I call concurrency is king. Because the read and write channels are independent, you can literally be doing reads and writes at the exact same time. Huge bandwidth boost.
And it goes further than that, doesn't it? Multiple outstanding addresses, out-of-order completion.
Yes. That's really powerful. A manager can send out new requests without waiting for the old ones to finish. And transactions, if they have different IDs, can finish in a completely different order than they were sent.
Which is great for parallel processing.
Massively improves system performance. Those transaction IDs are crucial. They let one single initiator port manage multiple logical threads simultaneously. It's very efficient.
Okay, so we've got the foundation, independent channels, concurrency, point-to-point. But where do things typically, blow up? You mentioned the handshake horror earlier. Those valid and ready signals seem so simple.
Deceptively simple. They are absolutely central to AXI.
Yeah.
That valid ready handshake happens on all 5 channels. The source drives valid high to say, hey, I have valid information, and the destination drives X ready high to say, okay, I'm ready to take it.
And the actual transfer happens on the clock edge when both are high?
Exactly. On the rising clock edge, when X valid and X ready are both asserted, the handshake completes and the transfer occurs.
Now, you mentioned rules, the sticky signals that are absolutely critical to prevent deadlocks. What are they again?
2 golden rules. First, the source must not wait for X ready to go high before it asserts its X valid. It has to be willing to put its data out there, even if the destination isn't ready yet.
Okay, don't wait for ready.
Second, once the source has asserted X valid, it must keep it asserted until that handshake actually happens. It can't just pull it back if the destination takes a moment.
So valid is sticky once asserted.
Exactly. And conversely, the destination is allowed to wait for X valid before it asserts X ready. It can wait until there's actually something valid to receive.
Seems logical. But where does the nightmare usually start?
Ironically, with violating that very first rule, the most common and critical protocol violation is when a master, the source, incorrectly waits for the subordinate's X ready signal before asserting its own X valid.
Ah, it waits when it shouldn't.
Exactly. The spec explicitly forbids it, and this seemingly small mistake can easily trigger a deadlock, especially if you have complex interconnect logic sitting between the master and slave. I remember one project, days spent chasing a stall, turned out to be one line of code in a custom IP, violating that don't wait for ready rule.
What?
Brutal.
Okay, what about write operations? There's another signal, WLS, right?
Yeah.
The last signal for writes. How does that cause trouble?
Oh, WLS starts as other classic. If the master doesn't assert WLS correctly on the very last beat of a write burst, the slave basically has no idea the transfer is finished.
It just keeps waiting.
Keeps waiting indefinitely for more data that's never coming. So it never sends the right response on the B channel, and the master might be stalled waiting for that response. Persistent stall. Total deadlock.
Have you seen that happen, like with vendor IP?
Absolutely. There was this AXI Stream Master demo from a major vendor. Turned out it just wasn't asserting TLST, the equivalent for AXI Stream, correctly under certain conditions. Data just vanished into the core. We spent ages debugging, pulling our hair out, needle in a haystack, all down to one missing signal assertion. Teaches you how vital every signal is.
And it's not always the master or slave directly, right? The interconnect itself can cause deadlocks.
Definitely. An interconnect might, for perfectly valid reasons like resource management, decide to hold ready low for a while. Now, if an upstream master is already violating that don't wait for ready rule, boom, instant deadlock.
So even if your IP blocks are technically compliant, the way they interact through the interconnect can lock things up.
Exactly. It highlights a systemic vulnerability. The system behavior emerges from the interaction, not just the individual parts.
And then there's that weird errata, right data arriving before the right address. That sounds counterintuitive.
It does, but AXI's independence allows it. The right ADA channel, W, can technically present data before the right address channel. ADW presents the corresponding address. While allowed, there's a known errata, where this specific timing can lead to corrupt or invalid data being written.
So what's the fix?
A common workaround is to basically enforce alignment between the channels in your design. Make sure a WVLID never gets asserted before the corresponding ACAVLID.
Which kind of defeats the purpose of the independence, doesn't it?
Well, it highlights what I call AXI's flexibility paradox. The protocol gives you this amazing independence for potential performance gains. But that freedom demands absolute meticulousness in managing the handshake signals like valid and ready across those channels. If you slip up, that flexibility turns into data corruption or deadlocks, not efficiency.
Makes sense. And of course, you can have simply failures too, right? Like a subordinate just timing out or a manager sending garbage.
Sure. Subordinate or manager failures, devices not responding within a timeout period, returning incorrect data.
Yeah.
Those happen. And you can also get into those nasty circular wait conditions, where component A is waiting for a resource held by B, which is waiting for C, which is waiting for A, complete system gridlock.
Okay, so when things do go wrong, AXI provides error responses. They're like diagnostic code.
Exactly. 4 key responses you need to know. Okay, binary 000, everything's good, normal access. XOK, binary 01, that's for successful exclusive access, a more advanced feature.
Then the error ones.
SLV error, binary CAN, that's slave error. The request got to the slave, but the slave itself had an internal problem. Maybe a FIFO overflowed, or it got asked to do something it doesn't support, like write to a read-only register, or it timed out internally.
So SLV points the finger at the slave device itself.
Precisely. And the last one is DSER, binary 11, decode error. This usually comes from the interconnect fabric. It means the address you sent. Nobody home. No slave exists at that address according to the interconnect's map. Essential in systems where not every single address is mapped prevents lockups.
So understanding these isn't just academic, it's crucial for debugging.
Yeah.
A self-ver tells you, look at the slave, while a deserter says, check your address map or the interconnect.
Absolutely paramount. They're your first clues. And remember, for write bursts, you get one response for the whole burst. For reads, you can actually get different responses for different beats within the burst, which gives you more detail.
And importantly, even if an error is signaled, the burst has to finish its specified number of beats, right?
Correct. The protocol demands completion of the beat count, even in the face of errors. No early termination of the burst on the bus itself.
All right, let's shift gears to burst blunders. AXI's efficiency comes a lot from bursts, multiple data transfers, or beats for one address request. Great for moving lots of data.
Huge for throughput.
And AXI supports unaligned transfers using byte strobes, WSTRB, right? Like starting a 32-bit transfer at byte address 0 by 1002.
It does support them, yes. But this is where a really hidden problem can bite you, especially with fixed bursts.
Okay, what's the catch with fixed bursts and unaligned starts?
With a fixed burst, the address stays the same for every beat. If that starting address is unaligned, say address 0 by 02 on a 32-bit 4-byte bus, then for the entire burst, only byte lanes 2 and 3 within that 32-bit data word are actually valid destinations.
So even if the bus is 32 bits wide, only 16 bits are active for that transfer.
Exactly. And crucially, this means your byte strobes, WSTRB, must reflect this. In that example, only WSTRB 3.2 should be asserted high. If you assert strobes for byte lane 0 or 1, that's a protocol violation. You're trying to write 2 bytes that aren't part of the valid unaligned address for that beat.
And that leads to
Incorrect data writes, potential corruption. It's hidden because a designer might think they're writing a full 32-bit word each beat, but because of that fixed unaligned address, only a fraction of the data is actually landing correctly, like pouring water into a sieve, as you said.
And I assume that has performance implications too.
Oh, absolutely.
Yeah.
The underlying hardware, like memory controllers, usually works with naturally aligned word boundaries. So when it sees an unaligned access, it often has to do extra work internally, maybe break it into multiple smaller aligned accesses.
More clock cycles, more latency.
Yep. Adds latency, eats clock cycles, directly hits your throughput. If you're only effectively transferring 16 bits on a 32-bit bus because of unalignment, guess what? Your effective data rate just got cut in half. Big performance penalty.
Okay, so besides fixed, what are the other burst types?
You got INCR incrementing burst. The address increases by the transfer size each beat. Perfect for reading or writing sequential chunks of memory.
Standard memory access.
Right. And then there's wrapping burst. The address increments, but if it hits a defined boundary, it wraps around back to the start. Then cache line fills.
Are there special rules for wrap bursts?
Yes. Wrap bursts have strict length requirements. They must be 2, 4, 8, or 16 beats long. And critically important, wrap bursts do not support unaligned starting addresses. Trying to start a wrap burst on an unaligned address is a definite protocol violation. Easy mistake to make.
Good to know. And what about other system-level constraints on bursts? I remember something about a 4 KB boundary.
That's a huge one, a fundamental rule. An AXI burst must not cross a 4 kilobyte address boundary. Why 4 KB? Because that's often the minimum size block assigned to a slave device.
So crossing it means you might be trying to talk to 2 different slaves within a single burst.
Potentially, yes. Or at least crossing into a region the first slave doesn't own. This will likely lead to an error, probably a deserve from the interconnect, saying, hey, the second half of this burst is going somewhere invalid. It's like trying to deliver a package across 2 different zip codes with one address label.
Makes sense. And, just to reiterate, once a burst starts, all beats must complete. No stopping mid-burst.
Correct. And worth noting, AXI Lite simplifies things by only allowing single-beat bursts. And AXI Stream, which is for data flow, doesn't use address-based bursts at all.
Okay, now for something maybe even more insidious. The silent killers. Clock domain crossing, CDC, and reset domain crossing, RDC. These aren't direct AXI protocol violations, but they can wreck AXI performance and reliability.
Absolutely wreck it. They are pervasive, often subtle root causes for design flaws that have a massive impact. CDC happens when signals pass between parts of the chip running on different unsynchronized clocks. RDC is similar, but involves signals crossing between logic elements reset by different asynchronous reset signals, even if they share a clock.
And the core danger here is something called metastability. What is that exactly?
Metastability is when a flip-flop, trying to capture a signal that's changing right at the clock edge, which happens often with asynchronous signals, gets stuck in an unstable in-between state. Neither a clear 0 nor a clear 1.
Like that traffic light stuck between red and green.
Exactly. And it takes an unpredictable amount of time to settle to a stable 0 or 1. If downstream logic reads the signal while it's in this metastable state, or if it settles too late, you get data corruption, misinterpretation, basically data incoherence or loss. Very dangerous for system reliability.
So how does this silent killer manifest in terms of AXI performance? It's not just about data errors.
No, the performance, it can be huge. First, throughput. The synchronizers needed to handle CDC safely at latency. We've seen cases like a 256-bit wide bus that should do 128 gigabase degraded by over 10% just due to CDC synchronization overhead. A 4K video decoder Vaza saw a 20% drop in effective bandwidth.
Wow. So your perfectly compliant AXI master or slave might be performing way below its potential just because of poor CDC handling somewhere else?
Precisely. It's silent because the AXI interface itself might look fine on a waveform, no protocol violations. But the effective performance tanks because of timing issues external to the AXI interface itself. It's not violating AXI rules, but the system context is killing its speed.
And it adds direct latency to transactions, too.
Yes. Every time a handshake signal crosses a clock domain, you need synchronization. A typical two-stage synchronizer, maybe running at 500 megahertz, adds about 4 nanoseconds of delay per bit being synchronized.
So for a full handshake across multiple signals,
It adds up fast. For a 16-beat burst, the cumulative synchronization latency just for the handshakes could reach, say, 70-80 nanoseconds. In some designs, that CDC overhead alone can account for more than 3/4 of the total write latency.
that's staggering. And that latency must cause other problems, like back pressure.
Huge back pressure amplification. Those cumulative delays ripple backwards, stalls upstream AXI transfers, messes up arbitration fairness, forces you to use much larger FIFO buffers to try and compensate.
And can it even look like an AXI protocol violation?
Yes, this is where it gets really tricky to debug. You might see an AXI master holding valid high forever, seemingly violating the rules because no handshake occurs. But the real root cause might be a massive delay buried deep in a CDC path downstream, preventing the ready signal from ever coming back in time. The symptom, stuck valid, is miles away from the cause, CDC delay. You end up chasing ghosts.
And verifying these asynchronous parts, like AXI bridges with CDC, must be incredibly hard.
Uniquely challenging. The asynchronous behavior means you can't possibly simulate every timing interaction. Formal verification tools are powerful, but sometimes they can only prove correctness up to a certain point, giving you an explored result, not a definite pass. Debugging the counterexamples they find requires really deep protocol and design knowledge. It's tough.
Okay, so if we're facing these potential nightmares, handshakes, bursts, CDC, what tools do we have? What's in the debugging arsenal? You mentioned a layered approach.
Right. The key takeaway is that no single tool or method is enough. You need to attack the problem from multiple angles, multiple layers of abstraction. Sometimes you need to look at high-level transactions. Sometimes you need to zoom right into individual signal waveforms. Sometimes you need software to control things while you observe hardware. Fixating on just one view, like only looking at waveforms for a streaming issue, often just keeps you stuck in the nightmare.
So where do we start? What about on-chip debugging tools?
Those are often your first line of defense. Yeah. Tools like Xilinx ILA, Integrated Logic Analyzer, or System ILA are invaluable. They're IP ports you put inside your FPGA design.
Like little logic analyzers on the chip itself.
Exactly. You can configure them to capture specific signals in real time, set up complex trigger conditions, and even get some AXI protocol-level decoding right in the waveform viewer. They sample at the actual design speed.
What about actively stimulating the AXI bus during debug?
That's where something like a JTAG to AXI master core comes in handy. It lets you, through the JTAG port, directly issue AXI read and write commands to talk to your slave devices on the chip, even if you don't have a processor running yet. Great for poking specific paths.
Okay, but what if the problem is on a really high-speed external interface or between chips? On-chip tools might not cut it.
Correct. For those really high-speed, complex interconnects, you often need external hardware protocol analyzers. Companies like Keysight, Teledyne, and LaCroix make these. They physically connect to your board, capture vast amounts of high-speed data, and provide really deep decoding and analysis capabilities for tracking down subtle system-level issues. Expensive, but sometimes necessary.
So that's the hardware debug side. What about preventing these issues earlier, during the verification phase? What methodologies help there?
This is where advanced verification techniques are critical. Formal verification is huge for bus logic. Instead of just running test cases, it uses mathematical methods to prove that your design meets certain properties, like adhering to the AXI spec. Assertion-based verification IP, FVIP, is a key part of this.
Proving correctness mathematically, not just through simulation.
Exactly. Then you have the Universal Verification Methodology, UVM. It's a standardized approach, usually using System Verilog, for building really comprehensive, reusable, and scalable test benches. It excels at generating random stimulus and checking lots of different scenarios automatically.
And tracking coverage.
Yes, that links to coverage-driven verification, CDV. You define what functional aspects need testing, and CDV tracks how well your tests are actually exercising those aspects, ensures you're not missing corner cases. And assertion-based verification, ABV, embeds checks directly in your design code to catch violations early during simulation.
Okay, let's bring this to life with some of those war stories. What are the common frustrations engineers voice about AXI?
Well, that valid-ready handshake comes up again and again. Some engineers really dislike that a destination can just halt the source indefinitely by holding ready low. They see it as potentially causing catastrophic error propagation, undermining quality of service guarantees.
And just the overall complexity.
Yeah, you hear things like AXI is 100 times more complicated than it needs to be, or it's a trap compared to simpler interfaces. Some even find things like data arriving before address just dumb, even though, as we said, it's part of that flexibility design.
I have also heard complaints about vendor examples that sometimes the starting code they provide is actually broken.
Unfortunately, yes. It's a common complaint, particularly with FPGA vendors. People report finding bugs, especially handshake issues, in the example AXI designs or AXI stream demos provided. They end up having to debug the vendor's example before they can even start their own work, or they hunt for community-verified examples.
That sounds incredibly frustrating. Leads to that FPGA hell feeling.
Exactly.
Yeah.
Especially if you don't follow the advice to verify components individually first. Trying to debug AXI issues in a full complex system without knowing the individual blocks are solid is, well, hellish.
Can you share some specific nightmare scenarios? The really tricky bugs.
Oh, sure. There's the classic weird data corruption, seen on ZingFox, for example. You write a known pattern like dead beef, but you read back something slightly wrong, like 7 dad bead. Yeah. You check the software, it's fine. It inevitably points to subtle hardware issues, maybe a BRAM configuration mismatch somewhere, or a timing path that's just failing, but only under certain conditions. Nightmare to trace.
What about complete lockups?
Yep. Had reports of design lockup, whole system just freezes. Sometimes traced to a downstream component simply not responding, maybe due to its own internal error or a CBC issue. Sometimes even vendor support can't immediately figure it out.
And that AXI stream issue you mentioned.
Right. The data stuck in vendor core because TLS wasn't asserted seems minor, but data flow just stops dead. In video applications, you often see stalled channels because a FIFO runs empty under flow due to slow input, or there are data with mismatches, or maybe the input data source just isn't sending anything, preventing downstream IP from locking on.
What about resets? That sounds like another tricky area.
Definitely. The short versus long resets problem. You find an issue is fixed if you just reset one module, like a DMA controller, but it's not fixed by a full system reset. That often masks a deeper problem with how different asynchronous reset domains were designed and synchronized. It hints that the system isn't coming up cleanly from a full reset.
And that data before address errata, it really does cause problems in the wild.
It absolutely does. We've seen real-world deadlocks directly attributed to right data getting ahead of the right address signal under specific timing conditions. It's not just theoretical.
So pulling all these stories together, what's the big lesson?
I'd say it underscores the critical importance of robust verification, especially formal verification for bus logic. Don't just rely on basic simulation or even vendor-provided AXI verification IP, as those might not hit the tricky real-world corner cases.
And breaking the problem down.
Yes. Isolate and verify components individually before integrating them. Understand that AXI's flexibility demands strict adherence to the rules, especially handshakes. And realize that the interconnect itself, the thing meant to help integration, can sometimes be a complex black box that introduces its own problems and needs its own debugging focus.
Okay, so prevention is key. How do we avoid the nightmare altogether? It's about being proactive, right?
Exactly. The best way to debug an AXI nightmare is to prevent it in the first place. Meticulous design, comprehensive verification, turn it from potential nightmare into just a manageable design challenge.
So what are those non-negotiable design guidelines for AXI compliance, the absolute must-dos?
First, rigorously follow the spec for all channels, handshakes, arbitration. Second, hammer home those handshake rules. Never wait for ready before asserting valid, and always maintain valid once asserted until the handshake. Third, ensure WLAST is asserted correctly on the final beat of every write burst. Fourth, respect that 4 KB address boundary for all bursts. These are foundational.
What about handling the inevitable traffic jams, back pressure, buffers?
Crucial. You need robust back pressure mechanisms so downstream modules can signal, hold on, I'm not ready, without data loss. That means adequate FIFO buffering, especially across clock domains, to absorb temporary stalls.
And aligning data, does that really help much?
Proper buffer alignment significantly boosts efficiency. Aligning your data buffers in memory to the natural boundaries expected by things like DMA engines minimizes those costly unaligned accesses we talked about. AXI can handle unaligned, but aligned is almost always faster. Worth the effort.
How do we squeeze out the best performance latency and throughput safely?
Judicious use of pipelining adding registers strategically can help close timing at higher clock frequencies. And leverage AXI's burst capabilities. Use INCR or wrap bursts whenever possible, and try to make them as long as practical to maximize data moved per address request. Longer bursts can also help amortize some of the CDC overhead.
And on the verification side, what's the recommended toolkit?
It's a combination. Formal verification, using AXI-specific formal VIP, is highly recommended for the core bus logic. UVM-based simulation provides that scalable, random, coverage-driven framework for broader functional testing. Assertion-based verification catches violations early in simulation. Coverage-driven verification ensures you're testing what you think you're testing.
And don't forget system-level tests.
Right. Simulate your design connected to other realistic components, like a processor system, under heavy traffic. That's often where interconnect-related bugs or subtle interaction issues surface.
And specific focus on CDC-RDC.
Absolutely. A dedicated CDC-RDC verification strategy is essential. Static checks for structural problems, precise timing constraints for the tools, dynamic simulation with metastability injection enabled, and assertions specifically designed to check data stability across clock domain boundaries. Sometimes harmonizing clock frequencies or using adaptive synchronizers can help mitigate the performance hit too.
Finally, any specific design patterns to avoid deadlocks?
Classic deadlock avoidance strategies apply. Resource ordering. Always acquire resources in a fixed order and release them in reverse order. Atomic locking. Grab all needed resources at once, or none. There are specific techniques like DLS, deadlock avoidance by least stalling, for on-chip buses. And fundamentally, design your system architecture to prevent circular dependencies from forming in the first place.
So at the end of the day, is just following the AXI spec enough?
Based on all these issues, the misaligned bursts causing hidden problems, the massive impact of CDC, the quirks in vendor IP, I'd argue that just meeting the base AXI specification isn't quite enough for guaranteed reliability in a complex chip.
It needs something more.
Yeah, I call it a standard compliance plus approach. You absolutely follow the spec, that's the foundation, but you also have to proactively anticipate and mitigate these complex interactions and side effects that occur in real-world SOLIS environments. Think system-wide, think about timing, think about how components interact through the interconnect.
Okay, so we've really journeyed through the AXI landscape today, from its powerful concurrent architecture to the potential nightmares, failed handshakes, burst blunders, those silent killers like CDC and RDC that can just cripple a complex system on chip.
And we heard from the war stories that reactive debugging, trying to fix these problems after they appear, is just incredibly costly and time-consuming, a real battle.
But the good news, the path forward, seems clear. It's about being proactive in design and verification.
Absolutely. Rigorous adherence to best practices.
Yeah.
Nail those handshake rules, manage burst alignment carefully, respect address boundaries, and complement that with truly comprehensive verification. Formal, UVM, assertions, coverage, system-level tests.
And paying meticulous attention to those cross-domain crossings, CDC and RDC, because they can silently degrade performance and even mask the true root cause of what looks like an AXI protocol violation.
Couldn't agree more. They need dedicated attention.
So as you, our listener, go about your day, maybe think about this. Mastering something like AXI isn't just about memorizing a spec sheet. It's about building a deep intuition for how it behaves in complex systems.
Yeah, learning from the past, mistakes, those war stories, and adopting robust practices really can transform AXI from that potential nightmare into a powerful, reliable tool for building the next generation of amazing chips.
And here's a final thought. What systems are around you right now, maybe even the device you're listening on, that rely on these incredibly intricate communication principles? And could similar silent killers be lurking beneath the surface, subtly influencing the performance and reliability you experience every single moment? Something to ponder.